Let's add a tiny bit more detail to the idea of biogeochemical feedbacks at glacial interglacial timescales. We are now convinced that there is about 100 ppm change from glaciation to deglaciation and vice versa, decreasing during glaciation. All the data is interpreted using oxygen isotopes, as we mentioned, O18, and also deuterium, which has hydrogen, and then deuterium, which acts pretty much the same way in terms of evaporation, freezing, etc., which one gets preferentially taken up. So fractionation is very common in nature, including biological processes like photosynthesis, which fractionates C12 versus C13 in organic matter, for example. Okay, so there are physical processes which fractionate, like evaporation and precipitation, and there are biological processes which fractionate during photosynthesis. Here comes my chopper. So the main point out of the glacial interglacial timescale, BGC, or biogeochemical cycle. By the way, BGC is a short form for biogeochemical cycles, mostly used by oceanographers, because atmospheric people don't talk so much about BGCs. Not much life in the atmosphere in terms of photosynthesis. It's considered as a land, terrestrial vegetation ecosystem process. Okay. So this is looking at the thousands of years before present, going from 9,000 to the last glacial maximum. This is the Antarctic cooling period, I think. Antarctic, let's say, should be age of the ice, and yes, okay. Where is it? Scale. Antarctic cold reversal, sorry. So you can see that the deglaciation started, we started warming, and then we had the little Younger Dryas episode, and then we came out and we are started the Holocene in journey here, and this is the CO2 going from about 190 ppm or so to 270 ppm or so. So this is very well established now as a observed fact, but the explanations are many. But we can connect it to what we said before in the relation between Vostok ice core data in terms of temperature and CO2 being much more close in the southern hemisphere than in the northern hemisphere. That has led to more of the explanations than anything else. So looking again, if you look now at the same period going from 25,000 to the current, this time scale is going this way. So you have the deuterium, delta O18 here again, and you can see the blips we have seen, and we have the Holocene here, and the isotopic records of terrestrial organic carbon delta C13 can be seen here to have growth of terrestrial biosphere as part of the solution for CO2 change. So does it match here? Not quite, right? So maybe human beings, agricultural communities, and so on have had a bigger impact already on CO2 concentration starting here at the end of the last deglaciation. So people like Bill Ruddiman, paleoclimatologist, do argue that humans started perturbing the carbon cycle from the time that we became agriculturalists and pastoralists in the Holocene from hunter-gatherers. But definitely I hope that it's clear how to interpret delta C13. When you have less CO2 in the atmosphere, plants who want to photosynthesize will take any carbon that's available, so they will take more of the C13 even if it's energetically expensive, and when there is more CO2 available, they will preferentially take more of the 12C, which is lighter, easier to assimilate into photosynthesis. So the depletion of C13 in the past organic matter can be interpreted as variations in the atmospheric CO2. That's what this is basically saying. But this gives you a good sense of the biospheric carbon cycle feedbacks, and this is the Antarctic climate record here. The main message to take again is that it doesn't necessarily explain the entire CO2 record. CO2 change from glacial, deglacial change. So just terrestrial biosphere doesn't do it. Ocean invoked again. This is from Karen Kofel's paper, who was actually a friend, is a friend from Simon Fraser University up in British Columbia, I think. She does a lot of this glacial, deglacial CO2 stuff. So she's showing some schematic of the potential circulation changes at the phases of the glaciation that we can see here. So we saw one before in the context of thermohaline circulation. So here she's showing what happens in the interglacial period of the last Eemian going to 118 to 127,000 years ago. You would have had the Antarctic bottom water formation, North Atlantic deep water formation, and the return flow happening here. So you're in the warm period here. During the inception stage, about 105 to 114,000 years ago, you would have started the polar cooling in both hemispheres, and you would have started perturbing the formation of the deep water and the circulation a little bit. But in the middle of the glacial period, 59 to 68,000 years ago, you would have had significant impact on the deep water formation here. Okay, so this is what we saw before. So you can see that the circulation changes, which means the CO2 uptake and the CO2 uptake in both hemispheres and its storage in the ocean in terms of dissolved organic or dissolved inorganic carbon, or is total CO2, would have been seriously affected. And what is added here as an explanation that is often invoked is that when you have a glacial period, as we saw, rainfall is reduced by various amounts everywhere, and we saw that it's pretty much not increased anywhere during such a glaciation, which means the Earth as a whole is very dry. And again, considering the Southern Ocean, dust deposition would bring some iron into the ocean, and iron is a micronutrient that is often lacking. We mentioned it briefly as the high nutrient, low chlorophyll regions of the world, where Southern Ocean is one of them. East Pacific around Galapagos is the other one, where lots of nitrogen is available, but it's not utilized because iron is missing and photosynthesis is inhibited because of that. So if there is a natural iron fertilization because of glaciation, that could take up more CO2 to explain the drawdown during glaciation. But this again doesn't explain the 100 ppm that we need. So it's possible that there are multiple processes happening, like terrestrial biosphere, iron fertilization. Maybe sea level changes a lot, so you would change phosphorus availability as well in the marine ecosystems. Corals would be affected as well, and so on. So this is again looking at atmospheric CO2 going from the past. Let's say we start from the last interglacial around 125,000 years ago, the so-called Eemian that we looked at. You would draw down CO2 over time, and then it would belch it back up by about 100 ppm from 180 to 280, 90 to 100. Okay, so iron flux to Antarctica, on the other hand, has varied. So here is the mid glacial period here, and this is towards the end. So does it explain this increase in terms of a drop in the ion flux and reduced photosynthesis? Maybe. The other one is called the Southern Ocean Amplifier. So the Great Southern Ocean Stratification, because of the deglaciation, may have lowered atmospheric CO2 concentration and prolonged ice ages. Again, you can see may have. So obviously these are speculations, but this is again showing how glaciation would have changed the ventilation of the ocean and the CO2 uptake itself. Okay, so you would have changed the circulation, and this also relates to the shifts in the polar front, subantarctic front, and the subtropical front, which I think is one of the favorite ideas of Robbie Taugweiler. There has been a little ice age in the 16th, 17th century that ended during the beginning of the Industrial Revolution, going from medieval warm period to the Little Ice Age. And that is related to the minima in solar radiation because of the minima in sunspots. So you can see the forcing, solar forcing, and there was also volcanic forcing, which may have initiated the end of the medieval warm period. So the CO2 signature associated with that is there, but it's not very strong. I think it's about 7 ppm. So Little Ice Age is not being very useful in terms of giving us clues about CO2 carbon cycle feedback processes during glacial, deglacial cycles. Little Ice Age was not global to the best of our knowledge, heavily concentrated in the European sector for whatever reasons in terms of internal feedbacks, but the drivers are better known in terms of enhanced volcanic eruptions starting the cooling end of the medieval warm period, and then the sunspot minima providing further radiation perturbation. The end of the Little Ice Age is still not completely understood, but there is an increased solar forcing, but also Industrial Revolution is argued to have put more pollution into the glaciers and accelerate their melt. So that also is reproduced in models with all those sorts of forcings. So it's basically the CO2 change during glacial deglacial seems to be combinations of several processes and not just the ocean uptake or the terrestrial biosphere response.